Well, it's Friday evening here. We're starting our new experimental format. It's called Lao Fei Talks. By the way, this is Ilya. Well, I guess we should start by introducing ourselves, right?
My name is Ilya. Right now I'm the CTO of LaoFei. Together with Fedor, we're building a really cool composites project, and before that I had more than 10 years of experience in composites, especially thermoplastic composites. That's exactly why we all gathered here together and decided to share what we know and what we think.
Actually, the idea behind this format is to have casual conversations about composites, because, as is often the case, the most interesting insights and thoughts tend to come out during relaxed, informal conversations. Summer has now arrived in Suzhou. It's really quite hot.
Now, we still have some time before real summer in Suzhou.
Yeah. This still isn't summer.
This is late spring.
30 degrees isn't summer yet.
Yeah. When it hits 35, then we'll know summer finally came.
So, Ilya, why composites?
Honestly, I don't know. Life just kind of worked out that way. I think for some people it's a conscious choice, but usually there's always some element of randomness. A long time ago, I was discussing this with an older colleague of mine. He was trying to convince me that there are no accidents in life, that everything is predetermined. And I was trying to explain that actually it's not like that. Life just throws a lot of opportunities at you. You choose something. And at some point, I got this idea when I had just started my master's program. And they told me, look, there's this cool idea. We need pipes for hot water, high pressure, high temperature, and epoxy is easy enough for that. And obviously they should be composite pipes because metal conducts heat and loses heat. So let's make composite ones. And I was like, okay, composite. But how? What? Why? And they said, we'll make thermoplastic with basalt. It'll totally survive 150 degrees and 20 atmospheres, no problem.
By the way, it's not immediately obvious, not at all clear really, that pipes for
hot water.
For hot water.
Regular utility pipes.
And they make them composite to reduce heat loss?
Yeah, to reduce heat loss, but mainly because of corrosion. Pipes rot away.
Ah.
A lot of people think they're stainless steel, and pipes should obviously be stainless steel, otherwise they'll rust. But obviously most pipes are just steel and they rust. That's actually a huge problem.
Corrosion, right? You know what I mean?
Yeah.
That's really one of the fundamental advantages composites have over metals. But first of all, it's a property of polymers. Polymers simply don't corrode the way iron does.
Iron and aluminum. Aluminum hates salt mist. Aluminum in salt water. Aluminum in the sea. That's actually dangerous. You really shouldn't use aluminum in the ocean. But a composite will all die and the composite will still float there.
Yeah.
Partly that's a problem, partly it's a solution.
No, it's...
Depends how you use it.
That's not a problem at all. Let it float and then we'll recycle it later.
Good point.
So tell me, how do you personally define what a composite is? And what exactly is a polymer composite?
Let's start with the obvious thing. Nobody actually knows what a composite really is. For ourselves, we chose a format where we mainly work with polymer composites, so we focus on them. A polymer composite is actually pretty simple. Generally speaking, there's a polymer matrix and there are fibers. The fibers are strong, high modulus. They carry all the load, while the polymer just distributes that load. If you take an ordinary thread, you can't use it like a beam. You can't stand it upright like a pole, it just collapses.
You can tension it, though.
Yeah.
But you can't compress it.
You can't even just stand it up like a pole because it immediately falls over. It has no compressive strength.
Yeah.
It's thin, but what can we do? We can coat it with polymer somehow and get a composite. And what does the polymer do? Basically, it redistributes the load across all the fibers at once. And suddenly we get something unique. The properties immediately improve and we get a material with something special. Back in the day, we argued a lot about what a composite actually means by definition. And the most important thing, I think, is that a composite should create some new properties. Neither the polymer nor the fiber alone has them. Each has its own set of properties, but together they create something unique, something neither could provide alone. And that's the key point.
Yeah, that's actually a really great definition. If I'm not mistaken, that's what's called synergy, right?
Yeah.
A composite is a synergistic material.
We combine several things and suddenly we get something neither of them had on their own. Thread can't handle compression. Polymer alone is weak and not stiff.
Yeah.
We combine them and get something entirely new.
There's this classic definition from Wikipedia. Wikipedia tells us that a composite is an artificial material.
Oh, okay, but there I'm already ready to argue with you.
Consisting of two or more separate components in combination.
Yeah.
With a clear boundary between them.
Yeah. A clear phase boundary is fundamental. Otherwise, we'd never distinguish a composite from an alloy.
Yeah.
But the part about it being artificial is debatable.
This is actually very debatable, mainly because all living things, in fact, are made up of polymer composites.
My favorite example is Nacre, which is also called mother of pearl. Mother of pearl is probably the coolest material, at least from a structural standpoint. So, what exactly is nacre? It's a reinforcing phase that is made up of many tiny platelets stacked together like bricks in several layers. Each layer is shifted about half a length compared to the one below it. This creates a proper brick pattern which gives the material its impressive strength. And to make it even stronger, they have these tiny little protrusions, kind of like interlocking joints that hook together, and all of it is filled with collagen. I mean, how is that not a composite? It's a real polymer composite, inorganic phase inside, polymer matrix around it, and nacre has unique properties. It's very hard, very stiff, and has huge fracture toughness. There's a whole body of scientific work around this. Everyone's trying to replicate nacre. Even I tried working on this topic once.
And it's beautiful too.
Yeah, and the optical properties, those become interesting because of it too.
All plants are built on the same principle. Cellulose fibers with lignin as the matrix, right? Cellulose acts as the fiber. Classic polymer fiber plus polymer matrix. Honestly, I think the best example of a composite is the trunk of a tree.
Yeah, it's a unique thing.
That very composite, which we relied on so heavily, became our primary building material, serving as the backbone of our construction.
Yeah.
The one half of civilization was built from.
Why half? I think all civilization started when we picked up a stick.
Yeah, we picked up a composite bat and just went around, beating things.
The neighbors.
The neighbors. When the first monkey picked up a stick, all the others had to start working. We've been learning to work with wood for thousands of years. We always account for fiber structure when working with wood.
A beam for a ship is always cut along the trunk.
Everyone knows that wood has a natural grain. And metals, on the other hand, appeared much, much later.
Way later. First there was wood, then stone. There was the Stone Age.
And then
the Bronze Age.
And if we follow that Wikipedia definition, which says that a composite is an artificial material, then, as you might recall, everyone remembers those old mud houses, built long ago, that people used as homes.
A classic example, too.
Made from straw and clay, or, as we usually say, from sticks and, well, crap.
Yeah. Classic dispersed reinforcement, and it works really well.
Speaking of dispersed reinforcement, fibers can actually have different lengths, as well as different orientations and arrangements. For instance, these fibers may be short or long, straight, aligned, or even twisted. And actually, one of the key concepts in composite mechanics is what is called the critical length. This critical length is an important idea in understanding how fibers reinforce materials.
Well, specifically for discontinuous fibers.
Why only for discontinuous ones?
For continuous fibers, it kind of exists and kind of doesn't. There are beautiful experiments where they take a single fiber, or almost a single fiber, a tiny roving, like a 1K toe, embed it into a composite and pull it. And at some point, if you polish the sample afterward, you can literally measure the critical length physically, because you can see how the fiber fractured into fragments of critical length. Those are really beautiful works, by the way.
So, what exactly is critical length?
Strictly fundamentally, critical length is the fiber length at which we can't distinguish a discrete fiber from a continuous one. Effectively, anything continuous is fiber longer than critical length.
Yeah.
If we take a fiber 200 millimeters long or a meter long and make a sample, we might not feel the difference.
There's a very interesting point here that I want to highlight. You see, critical length means that if the fiber is actually longer than a certain specific value, then the fiber's strength will be fully
realized, yeah.
Yeah, so the fiber will actually break, not the binder. That is exactly what we want to happen. Now, for carbon fiber in an epoxy binder, the geometry is quite clear. Carbon fiber diameter is about 7 microns, or sometimes 7 to 8 microns. The theoretical critical length is roughly a millimeter.
Yes.
So these are actually very short fibers.
Yes.
Practically speaking, the actual size is of course larger, but it's also not as though we really need to use meters for this purpose. However, the real question that comes up is, why are composites that are made from chopped fibers, which are short, still so much lower in strength compared to those made from continuous fibers? Let's think about that for a moment.
There are two basic things. First is, above all, orientation.
Yes, that's right.
That's the most important thing. Second is all those stories about interface interaction, but really only orientation matters. When you work with fiber a millimeter long, the chances of orienting it along, you can probably make a film, or you can make a thin thread where everything will be oriented, but how do you make a sample, a large panel, so all the fibers are aligned in one axis? Well, it's practically impossible.
Yes, this is what I consider key, because theory tells us that even if we have chopped fibers, but they're all perfectly aligned in one direction, then in that direction, there will be very high strength. The same as if the fiber were continuous.
But we can't do that.
But we can't do that because we can't orient chopped fibers like that. When we make the material, they'll still somehow turn in different directions, mix up. But actually, what do long fibers give us? They give us the ability to orient them as we need. And this is really the key point here. All of the strength, all of the effectiveness is found exactly in this orientation, in how we position them, in the fact that we focus the energy density in one direction. When we pull, the molecules stretch out, orient, the energy density focuses in one direction, and we make a thread.
Well, yes.
It's in this orientation that the strength lies. If you were to ask me what strength is
in orientation.
Strength is in orientation.
Well, naturally, there's the old concept of design for manufacturing, when we design a part for the manufacturing method, and usually it implies that we'll turn this, we'll mill this. But a composite is the kind of thing where we design the material for manufacturing. We immediately understand that, well, we can make a quasi-isotropic plate, we can then mill it. No, it's stupid. Well, it's as if we don't understand why we're doing it. It's some kind of black aluminum. The weirdest thing ever. We created a material that's isotropic in all directions, the same everywhere, then we cut our little part out of it. Why? No idea. Sure, it's lighter than aluminum. Nobody argues with that. Oh, it's like we just didn't think it through.
My favorite thing about anisotropy is this. We have 3 spatial directions. And a composite reaches its maximum strength when everything is aligned in one direction, let's say the X direction.
Yeah.
A composite is extremely strong precisely because all of the reinforcement is concentrated in just one direction, which really enhances its strength. Then, for example, we can mix material X and material Y together, and as a result, we get a new material called XY.
Yeah.
Then we can mix X, Y, and Z and get fully 3-dimensional reinforcement. And every time we mix things together, we lose performance. Unidirectional carbon composite can hit 3,500 megapascals, but once we go fully 3-dimensional, suddenly we're down near 100.
Yeah, it stops making sense.
It really...
Well, very rarely. Let's put it this way. Sometimes it still makes sense. Why do we need 3D reinforcement? The classic example is a fan blade, where mass matters more than anything. You can sacrifice almost everything, as long as it's light and still somewhat strong, and it'll still outperform metal.
Why?
Because you only have centrifugal force there.
Mass and centrifugal force. It's all about mass there. Actually, you reduce the loads.
Yeah.
That's actually cool. We just jumped to another fundamental property of composites, especially polymer composites. They're not just strong, they're also very light.
Exactly. And the blade is a perfect example. If we make a titanium blade, it'll be much stronger than a composite blade with 3D reinforcement.
Yeah, but it weighs 4 times more. Yeah, which means centrifugal loads are 4 times higher.
Exactly. So overall, you can find this balance, and actually it works really well. As soon as you make the blade composite, you remove all that excess mass, and formally the material may be worse, but in actual operation, for that specific application, it becomes better. That's important too. People often forget this. Composite isn't simply better than metal. The composites have...
I think they are better.
Better for what, though? Let's say ordinary carbon fiber polymer composite is terrible for a rocket nozzle.
Yeah, for a rocket nozzle, it's awful.
Every material has areas where it works and where it doesn't. Our job, anyone inventing something, is to understand what's actually needed where. And I think that's one of the major difficulties with composites. Not everyone understands how to work with them. It's complicated because you need to understand, okay, composites work well here. Aluminum works somewhere else. You make armor from steel, rocket nozzles from tungsten, but aircraft skin.
But why can we easily understand where wood is good and where iron is good? Yet with composites, it suddenly becomes difficult.
I think it's because composites are mechanically more complex. We already said there's Y, X, and Z, 3 axes. With metals, everything is simple. You open a handbook, take something like Aluminum 2024, it has there, I'm afraid to misquote it, but say around 450 megapascal strength, and you think, okay, 450 megapascals in every direction. You calculate equivalent stresses using von Mises, and any structure becomes easy to analyze. Very straightforward. But with composites, we suddenly have different strengths along different axes. Then we have shear properties, different stiffnesses, and asymmetry between tension and compression. You can't just use von Mises anymore, you need more advanced mathematics. And to use more advanced math, you actually have to think hard.
Interesting, actually. Do you know if anyone calculates wooden structures?
Yeah, they do. I even know real cases where wood wasn't just calculated. Wooden structures were modeled dynamically.
And by the way, it's interesting to note that some aircraft actually still use balsa wood even today.
Yeah, it never disappeared. Its density is like 0.4.
So what's unique about balsa? Just the density.
The density is honestly shocking. The first time I saw balsa, I grabbed a wooden block expecting normal weight, and it practically flew upward out of my hand because I didn't expect it to be that light. It weighs almost nothing. Sure, it's very afraid of water, but it's insanely light. For small aircraft, RC airplanes, model aviation, balsa is amazing. If only it didn't absorb water and become heavy afterward, I think we'd literally still be flying balsa airplanes.
Speaking of water, what about composites and water? We said they don't fear corrosion, but what about water itself? How does water actually affect composites?
Well, it's complicated. Generally speaking, they're not too afraid of it. You have to understand that composites vary widely. Like take epoxy resin. Everyone knows epoxy, at least from epoxy glue, but there are probably thousands of epoxy grades and they're all different. Some epoxies die if you heat them to 60 degrees and leave them under the Suzhou sun. And some epoxies survive 200 degrees without losing properties, holding that temperature for thousands of hours. So actually there are composites and polymers that don't really like water. They absorb water into their free volume. Properties decrease slightly, mass increases slightly. Polyamide, for example. Everyone knows nylon 6 fears water. Well, not fears exactly. It absorbs a lot of water and then it becomes inconvenient technologically. But the main problem is simply increased mass. Polyamide can absorb 2 or 3% water. And then there's something like PEEK.
So the mass increases by 2 or 3%?
For the pure polymer, yeah, that's right.
Probably not that scary, 2 or 3%.
Not too scary, until you imagine an airplane where one wing sat in the rain while the other stayed under a cover. Now one wing gained a few percent mass and the other didn't. You take off and the balance is wrong, the aircraft starts rolling to the right. Well, overall, generally speaking, most polymers don't really fear almost any chemicals. Alkalis, acids, ammonia, whatever else. For example, PEEK dissolves only in concentrated sulfuric acid, and there are very few applications that actually involve concentrated sulfuric acid. That's a very niche chemical industry case.
But there are some types of polymers out there that actually don't dissolve, even when you put them in something as strong as sulfuric acid, right?
Yeah, there are special polyamides, even special types of polytheramides, not ultim, but other grades from other manufacturers, that practically dissolve in nothing at all.
And that's actually another really cool advantage of composites. We choose both the fibers and the polymer, and we choose them specifically for the application. So it's not just one universal material that works well somewhere and poorly elsewhere, where we constantly need additives to improve some property. We can simply replace the polymer, if that's what the task requires.
Design, yeah. Actually, it's a kind of material design. We come in and say, okay, this will operate in extremely harsh chemical conditions under very high loads. Money doesn't matter. And then we go, fine, use the strongest fiber, say Torre T 1100, and the most chemically resistant polymer, some kind of polyethyramide or PEEK. Done, perfect. Next time the situation changes. Weight isn't that important. Well, it matters, but not too much. Now cost matters more. We need something cheaper and temperatures are low. Then we go, okay, let's use glass polypropylene. No high temperatures, everything's fine. Polypropylene, cost matters more, so use cheap glass fiber.
And that brings us to this variability. Different fibers, different matrices, different polymers, all combined in different ways to create different properties. And honestly, for me, this whole thing is really about complexity. The more complex the system is, the more degrees of freedom you have, the more possibilities there are, and the more room you gain. So, in a way, this is the price you pay for complexity.
Yeah, and speaking of complexity, that's exactly what we talked about earlier. Why is it often harder to create a composite part? Harder to design, harder to invent. The more complex the material, the more variability you have. Different fibers, different polymers. And on top of that, there are different manufacturing technologies, each adding thousands of constraints every time you need to choose technology, polymer, fiber, all while considering economics, the exact application, environmental conditions, and everything else. To do it really well, truly well, sure, you can make something that works, but it won't be optimal. To make it optimal, you have to.
Yeah, you need more degrees of freedom, which makes it harder.
You need to understand what your optimization criteria are, what exactly you're optimizing. You decide what matters most, then optimize around that. It's simply more difficult. You need a more holistic approach. You need more experienced specialists. You need people who truly understand. You need both a designer and a manufacturing engineer. The engineer says what's actually possible, then the designer creates a structure that can realistically be manufactured. And after that, it all goes into production. So adding complexity limits you, because designing becomes harder. Creating something good becomes harder, but it also gives you an incredibly powerful tool. If you understand how to do it properly, you can create something unique.
And philosophically speaking, it's pretty obvious. The better something is, the more complex it tends to become. That actually reminds me of a funny little story. There's that well-known phrase, everything genius is simple. Do you know who actually said it?
No, honestly, I never thought about it. It always felt obvious, like everyone knows the phrase, but nobody knows where it came from.
It was Goebbels. Seriously. Everything genius is simple was Goebbels. And I remember we had this funny discussion once. I also used to think about how complexity is actually good. And we had this German marketing director. I told her, listen, I've got this brilliant idea to explain that everything genius is simple is actually nonsense because people think it's deep wisdom, but in reality it came from Goebbels. And she was like, oh no, let's definitely not do that.
Not exactly the best reference there.
Yeah, fair enough. Take microprocessors, for example.
They're insanely complex.
It's very complex. I mean, honestly,
Nobody fully understands how they work anymore.
exactly. They're geniuses, but they're also extremely, even remarkably complicated. And in engineering terms, genius often just means things are complicated.
Yeah.
It emerges gradually through increasing complexity, through gradual development and complication. And that's really what composites are in material science, the next level of complexity. Compared to metals, they're genuinely a higher level of complexity. But that complexity creates new opportunities. Yeah, it's hard. Yeah, it's not simple. Yeah, you have to learn. But that's exactly what opens up new possibilities. And honestly, I think the biggest problems in composites today all come from the fact that we're afraid of this complexity. We keep trying to simplify things.
Well, we're afraid because we don't understand it. I mean,
Yeah,
maybe some people understand it and fear it less, but those who understand less, of course, they're scared. How do you design something you don't understand?
so people say, let's just do it the old way.
Well, we've always done it like this.
No, we need to learn. We need to build up experience. Yeah, composites are hard. Nobody ever promised it would be easy.
It's a long journey, and sooner or later, everyone will go through it. Everybody knows Boeing started experimenting with composites long before they built the Dreamliner with its composite fuselage. They began cautiously exploring composites back in the 1980s. What is this stuff? How does it work? What are the properties? How do we even measure them? Back then, standards were only just emerging. At one point, there simply were no regulations, no standards for proper testing. Someone had to go through that whole path first. Actually, it's easier for us now because we're standing on the shoulders of giants.
True.
A huge part of the journey has already been completed. The hardest steps are always the first ones, and all those first steps were already taken before us. We just shouldn't be afraid. We need to push a little further forward. Honestly, taking the first step is much scarier than taking the 10th. Now we already know we won't fall apart. At this point, everybody understands composites do work. Now it's just about learning how to use them correctly. But 30 or 40 years ago, nobody was fully certain composites really worked. People believed they probably should work, but there were still doubts. And right now, I think we're at the stage where everything is changing very rapidly. Honestly, over the last 10 years, everything has changed dramatically.
And another example about complexity. You started with Nacre. That's an incredibly complex system. And in nature, all systems that evolved over millions of years, they all move toward greater complexity, right? From a tiny protozoan all the way to
us.
So I suggest we end today on this optimistic note. Complexity is opportunity. It's an opportunity we shouldn't fear. Composites are complicated, but that's exactly where the opportunity lies. There's still so much room to grow, so much left to explore. As we reflect on what we've discussed, let's remember that every challenge brings a chance for growth and discovery. Let's embrace the complexity ahead, knowing it holds the promise of innovation and progress for all of us. We need to overcome that complexity. We really need to stop being afraid of it. And I think in all our future conversations, we'll keep diving deeper into it, discussing that complexity, trying to unpack it and make it more understandable, more approachable for everyone.
Make it easier to understand.
Yeah, make it easier to understand, make it more approachable. Let me shake your powerful hand.
Episode
1. Honestly, I have to say, it really feels like it turned out pretty well.
But we'll be waiting for feedback from everyone. Likes, subscriptions, comments, all welcome.
All right, thanks everyone. Bye everybody.